Hello, today we are going to learn about the differentiation in mathematics. The concept of derivative and the subject of differential calculus had its origin mainly in the geometrical problem of determining the gradient of a curve at a point and thereby determining the tangent at the point. It forms a basis for the precise formulation of the fundamental concept like instantaneous velocity, instantaneous acceleration and the rate of change of one physical quantity with respect to another. The fundamental idea underlying the subject were first convinced almost simultaneously by Sir Isaac Newton and Gottfried Will. The subject was further developed by James Bernoulli, Joseph Louis, Lagrange, Bernoulli, Candy and others. Let f be the functionality defined by the NBD of a point A. If and only it exists finitely, then f is said to be differentiable or derivable at A. In this case, the limit is called the derivative or differential coefficient of f. It is denoted by f dash of A. Okay. The another approach of the derivative, let y equal to f of x be the continuous function of a comma b, where x belongs to a comma b. For delta x be a small increment given to x and delta y be the correspondent change in y. Then y plus delta y equal to f of x plus delta y equal to f of x plus delta x minus f of x. So delta y by delta x equal to f of x plus delta x minus f of y by delta x. So now derivative in open interval. A function f defined on a comma b is said to be differentiable on a comma b if it is differentiable at point of a comma b if f dash of c exists for all c belongs to a comma b. Derivative in closed interval. A function f defined on a comma b is said to be differentiable on a comma b if f is differentiable on a comma b and f is right differentiable on a and f is left differentiable on b. Now first theorem. If a function f is differentiable at a, then it is continuous at a. F is differentiable at a and f dash of a exists and is finite. Now the converse of the above theorem need not to be true. That is, if the function f is continuous at a, then it need not to be differentiable at a. Theorem 2. The constant function is differentiable on R and its derivative is equal to 0 for all x belongs to R. Derivative of some elementary real functions. The identity function f of x equal to x is differentiable on R and f dash of x equal to a, x belongs to R. F of x equal to x power n, where n belongs to n, is differentiable on R and f dash of x equal to 1, where x belongs to R. F of x equal to root of x is differentiable for all x greater than 0. F dash of x equal to 1 by 2 power x. F of x equal to e power x is differentiable on R and f dash of x equal to e power x. Then the derivative of f of x equal to a power x. So d by dx of 2 power x equal to 2 power x log 2. That is, if the derivative of the d by dx of a power x equal to a power x log a. That's it. Here a must be greater than 0. Now the derivatives of sin x, cos x and log x. Now for cos x it is minus sin x, tan x it is secant square x, and it cot x minus cosecant square x. So reverse is also possible. Like for secant x it is secant x tan x, cosecant x minus cosecant x dot into cot x. Now derivatives. D by dx of c equal to 0, where c is constant. D by dx of x is 1 dy dx of x power n is n into x power n minus 1. That is, if we have 2, it is 2 power 2 minus 1. Sorry, x square, it is x power 2 minus 1, that is x. Root x, 1 by 2 power root x. dy dx of e power x is e power x. dy dx of a power x is a power x log a. And the derivative of log x is 1 by x. And derivative of sin x is cos x. Cos x is minus sin x. Tan x is secant square x. Cot x is minus cosecant square x. Secant x equal to secant x tan x. Cosecant x equal to minus cosecant x cot x. Now, algebra of differential functions. We shall now discuss some important properties satisfied by differential functions. If f and g are two differential functions at x, then f plus g is differentiable at x, and f plus g derivative of x equal to f dash x plus f g dash x. So f plus g dash x equal to f dash of x plus g dash of x. So another theorem. If u and v are two differentiable functions of x, then u plus v is differentiable function, and dy dx of u plus v equal to du by dx plus dv by dx. If f is differentiable function at x and k is constant, then kf is differentiable, and kf dash of x equal to k into f dash of x. Product rule in differentiations. If f and g are two differentiable functions at x, then the product function f into g is differentiable at x, and fg dash of x equal to f dash of x into g of x plus f of x into g dash of x. Now, product rule versus uv rule. If u and v are two differentiable functions of x, then their product u into v is differentiable function of x, and d by dx of uv is equal to du by dxv plus u into du by dx. uv formula. This is uv formula. In centimeter cubes. Now fluid dynamics. When the shape of the fluid element changes with time, we say that the element is in dynamic condition, or in other words, the element is said to be flowing. Therefore, the fluid dynamics is essentially a study of fluid forces by virtue of its flow. The complete analysis of fluid dynamics involves complicated differential equations. Given all the technological developments and tremendous growth in scientific research, we are unable to arrive at the general solution for the fluid dynamics differential equations till date. Characteristics of the fluid flow. A fluid flow may be categorized as steady and non-steady flow, or unsteady flow. If the velocity of the flow at each point in space remain constant with time, the flow is said to be steady. However, the velocity of the fluid may be different at different points in space. Example, water flowing with a very small velocity in a river. If velocity of the fluid at a point changes with time, the flow is said to be unsteady beyond a certain velocity called critical velocity. Regarding a streamline flow, it's worth noting that streamline can be drawn only for a steady flow. It is the path followed by fluid particles. Tangent drawn at any point on the streamline indicates the direction of the instantaneous velocity factor of the fluid particle located at that point. Two streamlines never intersect. If they do, we can draw two tangents at point of intersection. It means that the fluid particle located at the point of the intersection must possess two directions of motion simultaneously, which is impossible. As the streamline do not intersect, there is no cross flow, normal to streamlines. A streamlined flow is not necessarily an ideal flow. When the flow is unsteady and non-uniform, the flow is said to be turbulent. It is characterized by eddy currents, resulting in loss of energy. There will be a cross flow of the fluid. If a drop of colored liquid is dropped, a stream of color will be along the line in case of laminar flow, but the entire liquid will look colored in case of turbulent flow. A laminar flow is realized when the liquid is highly viscous. A streamlined flow is not necessarily an incompressible flow. When streamlined are grouped together like planes, we call the flow as a planar flow or the laminar flow. Similarly, when the streamlines are grouped together like a tube, like a broomstick, we all the flow as tubular flow or tube of the flow. Remember that laminar flow and tubular flow, etc., are composed of streamlines. Now we will learn Magnus effect. When a spinning ball is thrown, it deviates from its usual path in flight. This effect is called Magnus effect and plays an important role in tennis, cricket, soccer, etc. By applying appropriate spin in the moving ball can be made to move in any desired direction. Consider a ball moving in a fluid without spin. If we take frame of reference with respect to center of mass of the ball, the streamlines of the air at the top and at the bottom of the ball are symmetric. The speed of the air at points equidistant above and below the center of the ball are same. So pressure at corresponding points is same and no lift acts on the ball. If a ball is moving from left to right and is also spinning about a horizontal axis perpendicular to the direction of the motion as shown in the figure, different points in sphere will have different speeds. For example, the highest point of the sphere has a speed of v plus rho naught and the lowest point of the speed is v minus rho naught as shown in the figure. Due to the viscous effects, the air layer in contact with the sphere will also be dragged along with it. As a result, speed of air just above the sphere is v plus rho naught and the just below the sphere is v minus rho naught, neglecting viscous losses in air and also neglecting the variations of the gravitational potential energy of air across the sphere. We can apply Bernoulli equation to top and the bottom of the spheres. Aerodynamic lift and motion of a spinning ball. The lift or upthrust experienced by an object during its motion in a fluid is called dynamic lift. If the object moves in air, this dynamic lift is called aerodynamic lift. The lift or upthrust experienced by an object during its motion in a fluid is called dynamic lift. If the object moves in air, this dynamic lift is called aerodynamic lift. Now, coming to viscosity, the property of a fluid due to which it opposes the relative motion between its different layers is called viscosity. A fluid friction or internal friction and the force between the layers opposing the relative motion is known as viscous force. A briskly stirred fluid comes to rest after a short while. The microscopic cause for viscosity is intermolecular electromagnetic forces. Because of this property, the water layer touching the walls of the container will have the velocity equal to that of the walls of the container. When the container filled with liquid is rotated about its axis with a constant angular velocity, after some time water also rotates along with the container because of this property. Can we rotate a water in a tumbler without viscosity? It is also observed that different fluids will have different levels of viscous effect. For example, water flows more rapidly than honey. So to say, the honey is more viscous than water, and in general viscosity in liquids is much larger than cross section than in gases. When water flows through the tube, velocity of the water throughout the cross section of the tube is not uniform. Velocity is maximum at the axis of the tube, whereas it is zero at the walls. If water were a non-viscous liquid, it is possible to send it through a pipe with uniform velocity throughout a cross section. In the case of an ideal fluid, viscosity is zero. Consider a liquid flowing at a steady rate on a horizontal surface. The liquid can be assumed to consist of a different horizontal layers. The velocity of the liquid at any point on any given horizontal layer is same, but the velocity of the liquid in layers perpendicular to the direction of a flow is different in different layers. The velocity of the upper layer of the liquid surface is maximum and that of the lower layer is lesser. Velocity of the liquid layers can go decreasing with increase in depth, and the deepest layer in contact with the horizontal surface is at rest. Hence, a velocity gradient exists in a direction perpendicular to the liquid flow. If a specific layer of the liquid is considered, the layer below it tries to decrease the velocity of the upper layer due to the cohesive forces between the molecules of the adjacent layers. In turn, the upper layer, moving with greater velocity, tries to increase the velocity of the lower layer. Thus, an opposing force comes into play, tending to decrease the relative velocity between the adjacent layers, like frictional force between two solids. This force is called viscous drag. It appears as if a tangential shearing force is acting between the layers. To overcome these shearing forces and to maintain a constant velocity between the adjacent layers, an external force is to be applied. If there is no external force, the velocity of the flow decreases and becomes zero. This process of the fluid, which opposes the relative motion between different layers, is called viscosity. It is an internal forces that exist between the adjacent layers of the liquid. Again, we will come through these points. The property of a fluid due to which it opposes the relative motion between its different layers is called viscosity, a fluid friction or internal friction, and the force between the layers opposing the relative motion is known as the viscous force. A briskly stirred fluid comes to the rest after a short while. The microscopic cause for the viscosity is intermolecular electromagnetic forces. Because of this property, the water layer touching the walls of the container will have the velocity equal to that of the walls of the container. When a container filled with liquid is rotated about its axis with a constant angular velocity, after some time, water also rotates along with the container because of this property. Can we rotate a water in a tumbler without viscosity? It is also observed that the different fluids will have different levels of the viscous effect. For example, the water flows more rapidly than honey. So, to say the honey is more viscous than water, and in general, viscosity in liquids is much larger than in gases. When water flows through a tube, velocity of the water throughout the cross section of the tube is not uniform. Velocity is maximum at the axis of the tube, whereas it is zero at the walls. If water were a non-viscous liquid, it is possible to send it through a pipe with uniform velocity throughout a cross section. In the case of an ideal fluid, viscosity is zero. Consider a liquid flowing at a steady rate on a horizontal surface. The liquid can be assumed to be consist of different horizontal layers. The velocity of the liquid at any point on any given horizontal layer is same, but the velocity of the liquid in layers perpendicular to the direction of flow is different in different layers. The velocity of the upper layer of the liquid surface is maximum and that of the lower layer is lesser. Velocity of the liquid layers goes on increasing with the increase in depth, and the deepest layer in contact with the horizontal surface is at rest. Hence, a velocity gradient exists in a direction perpendicular to the liquid flow. If a specific layer of the gas is considered, the layer below it tries to decrease the velocity of the upper layer due to the cohesive forces between the molecules of the adjacent layers. In turn, the upper layer tries to increase the velocity of the lower layer. Thus, an opposing force comes into play, tending to decrease the relative velocity between the adjacent layers, like frictional force between the solids. The force is called viscous drag. It appears as if a tangential shearing force is acting between the layers. To overcome these shearing forces and to maintain constant velocity between the adjacent layers, an external force is to be applied. If there is no external force, the velocity of the flow increases and becomes zero. This property of the fluid, which opposes the relative motion between different layers, is called viscosity. It is an internal force that exists between adjacent layers of the liquid. As a result of large number of experiments conducted by Newton, it is found that in the case of laminar viscous flow, the viscous force acts tangential to the laminar, and in such a way it opposes the relative motion between successive layers in contact. The magnitude of the viscous force in a laminar flow is observed to be proportional to I. Surface area of the lamina, velocity gradient across the lamina. When the flow is along xy plane, velocity gradient is calculated as dv by dz. If the velocity of the upper layer is v plus delta v, and the velocity of the lower layer is v, the relative velocity between them is delta v, and thus velocity gradient will be delta v by delta y in a directional normal to the flow. And when the flow is along the axis of the cylinder, velocity gradient calculated as dv by dr, radial direction. Now the streamlines are parallel to x-axis, and the flow can be assumed as the number of layers parallel to the river flow. Different lamina will have different velocities, as the lowermost layer sticks to the bottom. The maximum velocity in this example is seen at the free surfaces. The above relation is known as Newton's law of viscous force, and it is applicable to any viscous laminar flow. Here, the negative sign indicates the viscous force opposes the relative motion, and n is the constant for a given liquid called coefficient of viscosity, eta. Coefficient of dynamic viscosity is defined as the tangential force per unit area of the layer required to maintain unit velocity gradient. Regarding the coefficient of viscosity, it is worth nothing that it depends only on the nature of the fluid and is independent of area considered or velocity gradient. Practical application and uses of viscosity. A parachute descends slowly, whereas a stone dropped from same height falls rapidly. The viscous force of the air on parachute is larger than the falling stone because the parachute has a larger area than a stone. Hence, parachute descends slowly. To reduce the friction between moving parts in a machine, a lubricant is used. A good lubricant can be highly viscous material like grease. A flask containing glycerin and the other flask containing water. Both are stirred vigorously and kept on the table. As the viscosity of glycerin is larger than water, it will come to rest earlier than water. Raindrops are smaller in size, but from but falls from the great heights. As a result, they should acquire greater velocity and as a result greater momentum. But due to the viscous force offered by the air, they attain terminal velocity which constant. When the raindrop attains this velocity, it will have zero unbalanced force. The viscosity of the water affects the sedimentation process if water flows on the mixture of sand and gold particles. Lighter sand particles will be carried away further by water, but denser gold particles not so. Like this, gold and sand particles can be separated. The high waves in the sea do not continue for longer distance. The reason is these are opposed by the viscous force between the layers of the seawater. So the waves are damped or suppressed. Viscosity tests of blood are useful in medicines. The sedimentation rate of the blood cells or the viscosity of the blood can be used to diagnose certain diseases. Stokes' law terminal velocity. When a body moves through a fluid, the fluid in contact with the body is dragged with it. This establishes relative motion in fluid layers near to the body, due to which viscous force starts operation. The fluid exerts viscous force on the body to oppose its relative motion. The magnitude of this viscous force depends on shape and size of the body, its speed and viscosity of the fluid. Stokes established that if a small sphere of the radius r moves with speed v through a fluid of viscosity n, the viscous force acting on the sphere has the magnitude of F equal to 6 pi n RV. This law is called Stokes' law. This law is applicable. The quantity of the fluid is much larger than that of the sphere. Speed of the sphere is not very large and there should be no turbulence. Now we will read the Magnus effect again. When a spinning ball is thrown, it deviates from its usual path in flight. This effect is called Magnus effect and plays an important role in tennis, cricket, soccer, etc. By applying appropriate spin, the moving ball can be made to move in any desired direction. Consider a ball moving in a fluid air without spin. If we take frame of reference with respect to the center of mass of the ball, the streamlines of the air at the top and the bottom of the ball are symmetric. The speed of the air at points equidistant above and below the center of the ball are same. So pressure at corresponding points is same and no lift acts on the ball. If a ball moving from left to right and is also spinning about an horizontal axis perpendicular to the direction of motion as shown in the figure, different points in sphere will have different speeds. Attraction between two closely parallel moving boards. When two boards move side by side in the same direction, water in the region between them moves faster than that on the remote sides. In accordance with the Bernoulli's equation, the pressure between the boards is reduced and hence, due to high pressure outside, they are pushed towards each other. Similarly, keeping two sheets of paper parallel to each other, when air is blown between the sheets, they attract each together. Now oscillations. Any motion or event that repeats itself at regular intervals is said to be periodic. In some periodic motions, a body moves to and fro along a given path between two extreme positions. Example includes the vibration of a guitar string or a speaker cone, the swinging of a pendulum, the motion of a piston in an engine, and the vibrations of the atoms in a solid. Such periodic motions are called the examples of oscillation. In general, an oscillation is a periodic fluctuation in the value of a physical quantity above and below some central or equilibrium value. In mechanical oscillations, such as those cited above, the body undergoes linear or angular displacement. Non-mechanical oscillations involve the variations of quantities such as voltage or charge in electrical circuits or the electric and magnetic field in radio and TV signals. In this chapter, we will discuss only mechanical oscillations, but the techniques we develop are applicable to other kinds of oscillatory behavior. A body undergoes periodic motion as has an equilibrium position somewhere inside its path, and this position no net external force acts on it. If it is left free at that position, it remains rest forever. If the body is given a small displacement from that position, a force comes into play which tries to bring the body back to equilibrium position, gives rise to oscillations or vibrations. If frequency is small, we termed as oscillation, otherwise we call it vibration. Simple harmonic motion is a special case of oscillatory motion. A body is said to be in simple harmonic motion if it moves to and fro along a straight line about its mean position, such that at any point its acceleration is directly proportional to its displacement in magnitude, but opposite in direction, and is directed always towards the mean position. The displacement of the body is always be measured from the mean position only. The displacement of the body is always to be measured from the mean position only. The displacement of the particle is always directed away from the mean position. If A is the acceleration of the body at any given displacement, y from the mean position, A alpha y or A equal to minus ky. Consider a particle released from the edge A of a smooth hemispherical bowl as shown in the figure. The particle oscillates between A and B with C as the mean position. When the particle reaches C, the loss of potential energy is available at the end as kinetic energy, and it moves further to reach B. At B, its velocity reduces to 0 and the gravitational pulls back toward the mean position, and the above motion is repeated, resulting in the periodic oscillatory motion. Examples of oscillatory motion which are periodic: clock, sewing machine, pendulum, watch, atoms, and vibrations of the guitar. And examples of periodic motions which are not acceleratory are uniform circular motion, orbital motion of planets in the solar system. If k is the constant of proportionality and minus signs indicates a and y are always in opposite directions. So here minus sign indicates that it will go in both front to and fro motions. So like this we completed this chapter of oscillations. So thank you for watching. Liquid has a free surface of its own while a gas does not. Mechanical treatment of a fluid. In fluid mechanics, we study fluid at a macroscopic level. It is concerned with characteristics that can be observed and measured on the laboratory scale. We cannot resolve the motions of individual molecules by measurement in our laboratories, but we recognize that it is the aggregation properties of individual molecules that determine the behavior of the macroscopic element of the fluid. Our measuring instruments average has the behavior of very large number of molecules in the vicinity of a fluid. It means in fluid mechanics we treat the fluid as a continuous matter, which is true at a macroscopic level. A fluid can exert three types of contact forces: pressure force, viscous force, and force due to surface tension. Contact force exerted by a fluid on its surroundings. In reality, a fluid may exert all these three forces simultaneously, and considering the effect of all these forces at once can be very complicated. So it will be very convenient to deal with these factors at a time and then combine all these effects. For this reason, we are going to define a concept of ideal fluid in which intermolecular forces are absent. In fact, all ideal fluids cannot be realized in reality, also known as dry fluids. An ideal fluid cannot exert viscous force or surface tension force because the cause of these two forces in the existence of intermolecular forces. We picture a fluid element which is small enough to consider it as very close to a point size mass and large enough to measure its volume and mass on laboratory scale. Density of the fluid element is then defined as the ratio of mass and volume of the fluid. Then, therefore, density is the mass per unit volume, or mathematically, uh, limit delta V tends to 0, delta M by delta V equal to dm by dV. Remember that the density is a macroscopic property. We cannot define density of a fluid at molecular level. However, at microscopic level, rho can be defined as the continuous function of position within the fluid. In general, rho may or may not be uniform. When the density is not uniform, we can define average density as the ratio of the total masses of the fluid and its total volume. Density of the fluid determines the inertia of a fluid. A low density fluid like air requires less force per unit volume to accelerate it than does a high density fluid like water. Rho also determines the gravitational force per unit volume. Density varies with temperature and pressure. Variation of density with pressure at constant temperature depicts the elastic property of the fluid, and variation of the density with the temperature at constant pressure depicts thermal expansion properties of the fluid. Bulk moduli of liquids in general are high enough that we can neglect the variations of density at atmospheric pressures. Hence, most of the liquids at atmospheric pressure can be treated as incompressible. On the other hand, it is not acceptable to treat gases as incompressible at atmospheric pressure. Regarding density, it is worth noting that in case of homogeneous and isotropic substance, density is same in all directions. The dimensions of density are ml power minus 3 t power 0. The SI unit is kg per meter cube, while the CGS unit is gram per centimeter cube or gram per cc. 1 gram per cc equal to 10 cube kg per meter cube. When immiscible liquids of different densities are poured in a container, the liquid of highest density will reach the bottom, while that of lowest density will reach the top at a stable equilibrium. The interfaces will be planes. With rise in temperature due to thermal expansion, volume of given mass changes, and so the density of the substance changes inversely proportional to volume. That is, rho is inversely proportional to volume. Rho equal to rho naught by 1 plus RT. Bulk moduli of the substance is defined as delta P equal to delta minus delta naught equal to delta P by delta B. So some powers can be determined in dyne. 10 power 5 dyne equal to 1 Newton. Specific gravity or relative density. The most common fluid in our usage is water. Hence, it is customary to compare all the other fluids or solids with water. Similarly, to get an easier and qualitative comparison with water as to how denser or how rarer a given substance is, specific gravity is used. It is defined as the ratio of the density of the given substance to that water at 4 degrees Celsius. At 4 degrees Celsius, the density of the water is 1000 gram kilogram per meter cube. The atmospheric pressure and gauge pressure. The pressure of the atmosphere at any point is equal to the weight of the column of air of unit is equal to the volume of the column of air of unit cross-sectional area extending from that point to the top of the atmosphere. Manometer. What is manometer? Manometer is a device used to measure pressure of any gas contained in a closed vessel. It consists of U-tube having some liquid. One end of the tube is open to the atmosphere and one end of it is connected to the vessel containing the gas as shown in the figure. The pressure of the enclosed gas equal to the pressure at A equal to pressure at B. So P minus P naught equal to rho into GH. So P equal to rho GH plus P. P naught equal to rho GH plus P. The excess pressure P minus P naught is called the gauge pressure. Next, hydraulic mechanics. Whenever external pressure is applied on any part of the fluid containing in a vessel, it is transmitted undiminished and equally in all directions. This is called Pascal's law of transmission of fluid pressure and has many applications in the daily life. Basing on Pascal's law, devices such as hydraulic lift and hydraulic brakes are designed. In these devices, fluids are used for transmitting pressure. In a hydraulic lift, as shown in the figure, two pistons are separated by the space filled with a liquid. A piston of a small cross section A1 is used to exert a force F1 directly on the liquid. The pressure P equal to F by En is transmitted throughout the liquid to the larger cylinder attached to the larger piston of area A2, which results the upward force of P into A2. F1 by F2 equal to A1 by A2. This was the Pascal's law. So when this will exchange, F2 into A1 equal to A1 into F2. F2 into A1 equal to F1 into A2. Hydraulic brakes in automobiles also work on the principle of Pascal's law. When we apply a little force on the pedal with our foot, the master piston moves into the master cylinder and the pressure caused is transmitted through the brake oil to act on a piston of large area. A large force acts on the piston and is pushed down, expanding the brake shoes against brake lining. In this way, a small force on the pedal produces a large retarding force on the wheel. An important advantage of the system is that the pressure set up by pressing pedal is transmitted equally to all cylinders attached to the four wheels so that the braking effect is equal on all wheels. Forces on sidewall of a vessel. Force on the sidewall of the vessel cannot be directly determined as at different depths pressure are different. Consider a strip of width dx at a depth x from the surface of the liquid. The force due to the liquid on the strip is given by df equal to x into rho into g into b dx. This force acts normal to the sidewall. The net force is obtained by integrating the above equation. That is F equal to 1 by 2 rho g bh square. Average pressure on the sidewall. The absolute pressure on the sidewall cannot be evaluated because at different depths on this wall pressure is different. The average pressure on this wall is given as P equal to 1 by 2 rho into g into h, rho gh. Now, fluid subject to constant acceleration. A fluid contained in a vessel may be subject to the constant linear acceleration without any relative moment being created between different elements of the fluid in the vessel. The fluid orients itself to attain a new equilibrium position under the action of the acceleration. Although the fluid is undergoing an acceleration, it is moving with the appearance of a rigid body. The fluid is thus said to be in a state of relative rest in the absence of relative motion between different fluid elements. The law of the fluid statics is applicable. Consider a liquid containing in a vessel. While at rest, the free surface maintains horizontal level, but in the state of relative rest under a constant acceleration A, the liquid orients itself to maintain the inclination theta may be related to the magnitude and direction of acceleration vector by considering the dynamics of an element of a liquid. Liquid at rest, liquid under constant acceleration. Free body diagram of the element with respect to vessel. Consider a small element of size delta x and delta y at a position coordinates x, y as shown in the figure. From the free body diagram, we can write the equations of dynamic along the x-axis. Pressure difference in an accelerated frame. When a liquid is filled in a container, generally its free surface remains horizontal as shown in the figure. As for its equilibrium, its free surface must be normal to the gravity, that is horizontal. Now the container is accelerated. Due to the acceleration of the container, liquid filled in it experiences a pseudo force relative to the container, and due to this, the free surface of liquid, which remains normal to the gravity, now is filled as shown in the figure, and the normal to the direction effective gravity. The inclination angle theta of the free surface of liquid from the horizontal is given by tan theta equal to a by g, that is theta equal to tan inverse of a by g. A closed tank car filled with the water is accelerating on the horizontal track with acceleration a. In this situation, the constant pressure layers of the liquid are inclined at an angle theta equal to tan inverse of a by g. Some liquid is poured in a U table. When the U tube is at rest, the liquid stand at same level I both the limbs. The U tube is accelerated towards the right. This results a height difference h. Tan theta equal to a by h, that is h by 2. H equal to al by g. Now we will study Archimedes' principle. Principle of buoyancy. You might have noticed that a bucket submerged in the water weighs less than when it is in water. Similarly, any object submerged in a fluid appears to be way less than it does outside the fluid. Some objects float on the surface of the liquid. As the pressure in a liquid increases with depth, the upward pressure on the bottom surface of the object submerged in the liquid is greater than the downward pressure on the top surface of the object. This difference in the pressure causes a net upward thrust on the object. This upward force or thrust is called force of buoyancy. What is the cause of this force? This force of buoyancy is not a new kind of force. It is in fact a fluid contact force. Fluid pressure is the cause of this force. Force of buoyancy is defined as the resultant fluid pressure force acting on the immersed body. Forces of buoyancy acting on the body immersed partially or completely in a static fluid is numerically equal to weight of the fluid displaced and is directly vertically upwards. When a body is partly or wholly dipped into water, the fluid exerts a force on the body due to the hydrostatic pressure. At any small portions of the surface of the body, the force exerted by the water is perpendicular to the surface and is equal to the pressure at the point multiplied by the area. The resultant of these forces is called upthrust or buoyancy. To verify the Archimedes principle, consider a body immersed in a fluid of a density rho as shown in figure. The force on the vertical sides of the body will cancel each other. The top surface will experience a downward pressure F equal to A into P1, where P1 equal to P naught plus H in rho GH. Now flotation. When a body of density rho B and volume V is immersed in a liquid of density rho L, the force is acting on the body or weight of the body W equal to M into G, acting vertically downwards through the center of the gravity of the body. The upthrust B equal to rho Vg, acting vertically upward through the center of the gravity of the displaced liquid, which is also known as center of buoyancy. So the following then situations are possible when the body is released. So the following situations are possible when the body is released. Rho B greater than rho L. In this situation, W is more than B, and hence the body will sink normal to the free surface. Rho B equal to rho L. In this situation, W is more than B, and so here W equal to B. So the body will float while it is fully submerged. Rho B less than rho L. In this situation, W less than B. So the body will move upward normal to the free surface after some oscillation. It will finally settle in an equilibrium position while partially submerged. Then the new upthrust force on the body is B1 equal to W for translation equilibrium. A piece of ice is floating in water taken in a container. When what will happen to the level of the container when the ice just melts? Let mg is the ice be floating in the water of density 1 gram per centimeter cube. Then from the law of flotation, m equal to v into rho of ice equal to v into im rho water. So the final volume is equal to m by rho, that is m into centimeter cube. Okay, now we will learn chain rule. If y is differentiable function of u and u is differentiable function of x, then y will be differentiable function of x and dy by dx equal to dy by du into du by dx. This is called chain rule. The rule can be further extended. For example, if y is a function of u and u is a function of v is the function of w and w is the function of x, then x and y will be function of x, and therefore dy by dx equal to dy by du into du by dv into dv by dw into dw by dx. So assuming the property of a differential theorem. Okay. Now we will see another differential equations. D by dx of u power n is n into u power n minus 1 du by dx, and d by dx of root u equal to 1 by 2 into root u into du by dx. D by dx of e power x is e power u is e power u into du by dx. See, here two are the differentiable variables like u and n. If u is differentiable function of x, then based on chain rule we have the following useful results. These are the results. D by dx of log u is 1 by u into du by dx. D by dx of sin u is cos u into du by dx. D by dx of cos u equal to minus sin u into du by dx. D by dx of tan u equal to secant square u into du by dx. D by dx of cot u equal to minus cosecant square x in u into du by dx. Okay, another theorem. Let f belongs to a comma b and c comma d be the bijection and g is the inverse function of f. If f is differentiable, x belongs to a comma b and f dash of x not equal to 0, then g is differentiable and at f of x and g dash of f of x equal to 1 by f dash of x. Note: let f be the bijection if f is differentiable at x and f dash of x not equal to 0 and f power minus 1 is differentiable at f of x and f of minus 1 not into f of x equal to 1 by f dash of x. If y equal to f of x and x equal to f power minus 1 into y, then d by dx by dy equal to f inverse dash into y equal to f inverse dash into f of x equal to 1 by f inverse of x equal to 1 by dy by dx. Now another theorem: y equal to cos inverse of x is differentiable for x belongs to 1 comma minus 1 and dy by dx equal to minus 1 by 1 minus x square. Another theorem: y equal to tan inverse of x is differentiable on R and dy by dx equal to 1 by 1 plus x square. Y equal to tan inverse of x, where x equal to tan y and where x belongs to R and y belongs to minus pi by 2 comma pi by 2. Now we will study fluid mechanics. Fluid is a state of substance having the ability to flow liquids and gases. For example, liquids and gases are an example of fluids. Usage of fluids is an integral part of our life. Water covers the 3/4 of our Earth's surface. The branch known as fluid mechanics of physics deals with the study of fluids, that is fluids and gases. How we define a fluid? How does a fluid behave under external forces? What kind of contact forces does a fluid exert? What are the factors affecting the fluid contact forces? What kind of mechanical energy does a fluid possess? These are some of the questions the fluid mechanics attempts to answer. Matter may be divided into solids, liquids and gases. Liquids and gases together are classified as fluids. A solid has a definite shape and volume, not as they are not easily deformed by shearing force because of the cohesive force between the molecules. Liquids and gases do not have their own shape. A liquid can have a fixed volume but has no definite shape and take the shape of the container. A gas does not have a fixed volume and its volume depends on the volume of the container in which it is taken. Liquids and gases cannot sustain shearing force. Hence, an applied shearing force can cause the liquid or gas to flow. A substance that flows is called a fluid. An ideal fluid offers no resistance to the shearing force at all. Hence, a fluid is that state of matter in which the molecules are arranged randomly and the molecules in it are subjected to weak cohesive forces. Thereby, they offer negligible shearing force to its flow. A fluid can exhibit elastic nature under normal contact forces which are applied perpendicular to the surface of fluid. Fluids can be compressible or incompressible by the application of external pressure. If volume of the fluid changes, then it is compressible fluid. If the volume does not change, it is called incompressible fluid. We must remember that a substance may have the state of solid or the state of fluid depending on the external conditions. It is important to note that all the fluids have the ability to flow only when allowed to. When a fluid is not allowed to flow, such a fluid is known as static fluid, and the fluid is known as dynamic fluid if it is allowed to flow. It is not necessary that a static fluid must always to be rest. For example, water poured in container moving with uniform velocity will ultimately assume the shape of the container. Here, water is moving but not fluid, and so water is the example of the static fluid. Generally, it is very difficult to compress liquids, that is, bulk moduli of liquids are sufficiently large so that container can be treated as nearly incompressible for usually applied pressure. But gases can easily be compressed by applying pressure in the order of atmospheric pressure. Also, a liquid. The initial release of Java was nothing short of revolutionary, but it did not mark the end of the Java's era of rapid innovation. Unlike most other software systems, the usual settlement into a pattern of small incremental improvements, Java continued to evolve at an explosive pace. So, soon after the release of Java 1, the designers of Java has already created Java 1.1. The features added by Java 1.1 were more significant and substantial than the increase in the minor revision number would have you think. Java 1.1 added many new library elements, redefined the way events are handled by applets, and reconfigured many features of the 1.0 library. It also deprecated several features originally defined by Java 1. Thus, Java 1.1 both added and subtracted attributes from its original specification. Continuing in this evolution, Java 2 also adds and subtracts features. While all languages change over time, changes to Java take on an extra importance because older browsers will not be able to execute code that uses a new feature. For this reason, it is good to have a general understanding of which various changes have taken place. With this in mind, the next section takes a brief look at the evolution of Java since its original 1.0 specification. Version 1.1 added some important elements to Java. Most of the additions occurred in the Java library. However, a few new language features were also included. Here is a list of the most important features added by 1.1. Java Beans, serialization, remote method invocation, Java database connectivity, that is JDBC, Java native interface, reflection, various security features, built-in support for 1-bit character stream, significant changes to event handling that improve the way in which events generated by graphical user interface components are handled, inner classes which allows one class to be defined with another. The accessibility library provides features that makes it easier for people with sight impairments or other disabilities to work with computers. Of course, these capabilities can be useful for any user. The Java 2D library provides advanced features for working with shapes, images, and text. Drag and drop capabilities allows you to transfer data within or between applications. Text components can now receive Japanese, Chinese, and Korean characters from the keyboard. This is done by using a sequence of keystrokes to represent one character. You can now playback WAV, AIFF, AU, MIDI, and RMF audio files. The Common Object Request Broker architecture (CORBA) defines an object request broker and an interface definition language, that is IDL. Java 2 includes an ORB and IDL to Java compiler. The latter generates codes from an ideal specification. Performance improvements have been made in several areas. A just-in-time JIT compiler is included in the JDK. Many browsers include a Java virtual machine that is used to execute applets. Unfortunately, browser JVMs typically do not include the latest Java features. The Java plugin solves this problem. It directs a browser to use a Java runtime environment rather than the Java's JVM. The JRE is a subset of JDK. It does not include the tools and classes that are used in a development environment. Various tools such as Java C, Java, and Java Doc has been enhanced debugger and the profiling interface for the JVM are available. Although not as extensive as the deprecation experienced between 1 and 1.1, some features of 1.1 are deprecated by Java 2. For example, the suspend, resume, and stop methods of the thread class
should not be used in new code. Throughout this book, deprecated features are pointed out and their Java 2 alternatives are described. Um, this will be helpful to any programmer charged by updating Java 1.1 code. So, like this, we are discussed the Java topics and some mathematical topics. Thank you for watching the video.